Hi folks, Mr. Long here. We're going to continue on with this set of examples to get you ready for your first calculus assignment. And we're going to deal with the fundamental theorem of calculus that we've already gone over. We're also going to go over even and odd functions. This is a nice application of even and odd functions. So to begin with, let's do the FTC, the fundamental theorem of calculus. Okay, so the first thing we want to do, and by the way, it's the same function, so I just put in all the areas here, and we're just going to use those areas. Okay, so it says here, determine how much the y value of the original function, big F of x, which related to the given rate function, f of x, on the graph, how much does f at x change by from x equals 6 to x equals 12? Use proper calculus notation. Okay, so here's what we know. We know that we're going to go from, and I'll just put it there, 6 here, 12 here, so that becomes 12, and that's 6. Okay, so what we're doing is we're going to calculate the area between the rate function y value and the x-axis, between x equals 6 and x equals 12, and that's going to represent, right there, the change in y value. Okay, please look to the side where you can see that. So it shows it right here. Area under the rate curve is accumulation in y value on the original. Okay, area under the rate is equivalent to the accumulation or change in y value. Doesn't necessarily tell you the y value, but it shows you how much it changes by. Okay, so let's look at this example then. So what is the integral from 6 to 12? Well, the integral from 6 to 12 is the area under the curve from 6 to 12. So I'm going to highlight it in blue. So I want this right here, and there, and there. Okay, so if I'm going to add all these up, I know that the area, the integral from 6 to 12 of f at x dx equals the first integral, which is this one here, okay, that one there, and that integral goes from 6 to 8 f at x dx plus, then I need to do this integral here, which is the integral from 8 to 10 f at x dx. And then finally, I have to get the area from 10 to 12. Okay, and I want you to notice something here. So 6 to 12 is the same thing as 6 to 8 plus 8 to 10 plus 10 to 12. So whenever areas are joined this way, this starts at 6 and it ends at 12, that's going to be 6 to 12 because I'm going 6 to 8 and then starting at 8 over here. 8 to 10 and then I start again at 10 over here. So these areas are automatically beside each other. So the sum of all three of these areas adds up to that area. And that formula, folks, is right here. It's number 3. Okay, so what does this work out to then? This works out to, and by the way, we see right away that this area and this area are the same size and opposite sign. So in fact, what I can do is cross those out, those add to 0, and I'm left with this area of 10 to 12, from x equals 10 to 12, which is 8. So that's our answer. Okay, so the area from 6 to 12 f at x dx is 8. And what does that mean? That means that on the graph of big F of x, what it means is that there is an increase, and I don't know the shape for sure, but I know that the y value increased by 8 when I went from x equals 6 to x equals 8. Okay, so it might have gone down, right, and then gone back up. it might have gone way up and then come down, but the net increase, the net change, sometimes called a net change theorem, is 8, okay, is 8. Okay, so we know that. Then it says, given that f at 8 equals 10, determine f at 6. Now we're introducing the second part of this fundamental theorem. And the second part of that fundamental theorem is this. F at x equals f at a, that's known, and then the area from a to some number x. Okay, so in this case, I have that f at 8 equals 10. So now I have an ordered pair on the original. So I write this down. F at x equals f at 8 plus the integral from 8 to x f at t dt. And I know that change of variables is confusing. We're going to deal with that. I keep saying that later, but we will deal with it later. Okay, and do I know anything here? Right, all I did, by the way, is followed the formula. That's it. Right? If that's a, that's a. So if that's 8, that's 8. So now I should write it down with f at 8. What is f at 8? Oh, it's a y value of 10. So big F of x equals 10 plus the accumulated area from x equals 8 to some value x, f at t dt. Okay. All right, so now let's use that. So now instead of f at x, I want to find f at 6. So f at 6 will equal 10, right? But let's look at this. So this is x here, so that becomes x there. So it's going to be f at 10 plus the integral from 8 to 6 f of t dt. Now, there's something we should notice here. We don't like writing our integrals with a bigger number in the bottom, okay, from x equals 8 to x equals 6. That means I'm going from right to left. So what I should always do is reverse those, and then this positive will become a negative, right? So I rewrite that, and I say that I've got 10 minus the integral from 6 to 8, f at t dt. Okay, do I know what this area is? Because that's just area between the curve and the x-axis, between x equals 6 and x equals 8. Let's go over here and look. Between 6 and 8. There it is, between 6 and 8. So that's 6 and that's 8. I know that the signed area is negative 4. So it's going to be 10 minus negative 4, which is going to be 14. So that means f at 6 equals 14. Let's see if that makes sense. Okay, let's see if that makes sense. So I know at x equals 8, the y value is 10. Going backwards in time, I know the function was decreasing. Okay, so in other words, the function, the original function, was going downhill because this is a negative value, the rate. So if the y value here was 10 on f, this is on f, does it make sense that up here it's 14? Well, of course it does, because the function was decreasing. The rate was negative, okay? The function was decreasing. All right, let's do this one now. Same sort of thing as before. So we've got f at x equals f at a, and our f at a is still f at 8, which is 10, plus the integral from x equals 8 to some number x, f at t dt. Now, what do I want to figure out? I want to figure out f at 12. Okay, I want to figure out f at 12. So f at 12 will equal 10 plus the integral from 8 to 12 f of t dt. Okay, so I need to get the area between 8 and 12. The area between 8 and 12. Well, would you look at that? There's 8, there's 12. The total area is 4 plus 8, that's 12. Okay, so I go all the way across there and I go up. That is my signed area. So it's 12. So then since the area is 12, that means the y value on the original increased by 12. Okay, because the rate here is a positive. Okay, so now it's going to be f at 12 will be 10 plus 12. Again, this right here is 12, which is 22. So f at 12 is 22. Okay. Which again makes sense because if I'm starting here at x equals, I'm starting here at x equals 8. Okay, I'm starting here at x equals 8 with a y value of 10. And then the rate is positive. Okay, so in other words, snow is falling. Well, if I start with 10 centimeters of snow and the snow falls, 4 centimeters and then 8 more centimeters, clearly it's going to be deeper snow. Okay, so that does make sense. Okay, that's how you work the fundamental theorem of calculus. Okay, so let's see here. If the rate function f at x is even, draw that part of the graph. So we're done with our fundamental theorem. If the rate function f at x is even, draw that part of the graph between x equals -4 and x equals 0. What does even mean? Let's draw some even graphs. So if that part of the graph there looked like that, if the graph was even, it would look like that, right? So because the definition of even is that f at -x equals f at x. And we can see that numerically, right? Say that this is a y value of 2 here. F at -1 equals 2 equals f at 1. Okay? So when I reflect horizontally, I get the same y value. Okay? F at -x equals f at x. Okay? So it's just a horizontal reflection. That's all it is. So how do I do this one? How do I make a horizontal reflection? And I have to do it between x equals -4 and x equals 0. So it has to be a horizontal reflection. So what's the horizontal reflection of that shape? That shape. And then what's the horizontal reflection of this shape? Well, it's going to be the horizontal reflection. So let's see here. It goes over by 2 and then it goes down 4. So over by 2 and down 4. Okay, there we go. So now I've got an even function. Okay, I've got an even function, and that's what it looks like right there. Okay, so there's f at x. That's f at -x. There's f at x. There's f at -x. It's reflected across the y-axis. Okay, there's a reflection across the y-axis. Then the question is, what is the area from -4 to 4? Well, we already knew that this area here is 0.57. Let me write that properly. 1.57. And we know this area here to be 2 times 4 is 8, divided by 2 is -4. So altogether, what is the area over here? The area over here is, between these two, is -2.43, right? That's the total area. Well, if this area that we see here adds up to -2.43, what will the area be over here? Well, it's symmetrical. It has to be exactly the same. That's 1.57, so that's 1.57. This is -4, so this is -4. So if the total is negative 2.43, the total over here is also negative 2.43. So all I have to do is use some thinking and go, oh, okay. If it's even, for the even function, it's just going to be 2 of the integral from 0 to 4 f of x dx. So just do your area on the right side and then double it. Okay, and we knew our area is negative 2.43, so it's 2 times negative 2.43, which is going to equal negative 4.86 approximately. Okay, so again, that's what an even function looks like. Now let's try it with an odd function. Okay, so what do odd functions look like? Well, odd functions are things like x cubed is an odd function, okay? So it's reflected twice, right? So it's reflected, this part of the graph then reflects over to here, but then this part of the graph here reflects down to here. Okay, so I reflect horizontally, and then I reflect vertically. Okay, so that means that if I take, and if I want to bring it back, I take this part here, I reflect it vertically, okay, there, and then I reflect it horizontally, and it brings me back to where I was. So this is a case where negative x, f at negative x, and then I multiply that whole thing by a negative, and that gives me f at x. Okay, so it's 2 reflections, horizontal and vertical. So what it means is we can do this twice and see. So for this one, I'm going to reflect it horizontally, okay? Then I'm going to reflect it vertically. Same thing here. I'll take this part of the graph right here, and I will reflect it horizontally. It looks like that. And then I reflect it vertically, and it goes up here like that. Okay, what I'm going to do now, though, is take the highlighter and highlight it in blue what the actual curve is. That's the odd curve. So the odd curve looks like this. Okay, that's our function. Now what I'm going to do is shade in the areas I'm interested in. I'm interested in the area from negative 4 to 4. So that would be this area. Now, how is that area related to the area from 2 to 4? Well, it looks just like that. Equal in size, opposite in sign. Then I do the semicircle. Well, that semicircle is underneath. A semicircle of the same size is above. Well, look at that. So if we look at numbers, that's positive 4, that's negative 4, that's going to be negative 1.57, that's going to be 1.57. So altogether, the area from negative 4 to 4 is 0. Okay, so the area for an odd function will always be 0. Okay, if you're going from the same location, like negative 4 to 4, or from negative 3 to 3, or negative 1 to 1. Because of the symmetry, because of the geometry. Okay, the area will always be 0. So I didn't even, and that's a common thing that you'll get asked. And so people will take the time, just like I did right there, to draw the odd graph, and then they do the calculations and they find out it's 0, when I could have just simply said, if you were asked to do this calculation and you knew it was an odd function, you automatically just write 0, okay, because of the geometry. All right, folks, hopefully that helped. Definitely pause, rewind, go through that again, and best of luck in